Alright, hey guys, this is Mrs. Cribb. We're going to go ahead and do this tutorial on the additional honors notes from chapter 14. And so you'll notice here it's on reaction order, and for a particular reactant indicates how the rate of the reaction is affected by the specific reactant's concentration. So we're going to deal with reactants in an equation. The rate law is an equation that mathematically describes how fast a reaction occurs. So one of the examples that we might have here is 2 nitrogen oxide plus bromine. Remember, bromine's diatomic. Yields. Now most reactions are reversible, so you should start writing them with reversible arrows. Yields 2NOBr. Okay, this is the general equation, and so if we write the reaction law for it, or the reaction rate equation, you might call it, the rate equation rather, it's R equals, or R stands for the rate equals a constant, there's lots of constants in chemistry, times the concentration of the nitrogen monoxide to some power, and this time it was squared, times the concentration of bromine. Okay. Alright, what I want you to notice about this is a couple of things. First of all, you have NO and Br2. That is the reactants only. So the rate law deals only with the reactants. And so if I add nitrogen monoxide or bromine, how is it going to affect the rate? The R is the rate. Okay? The K is a constant. So let me give you another example, one that doesn't happen to have this 2. Notice this 2, the squared, it's the same as this one. That's just coincidental. So we're going to do one that doesn't happen to have that one. Okay, let me see if I can find one on here. We have 2 hydrogens plus 2 nitrogen monoxide yields nitrogen plus 2 moles of water. And the rate law for that would be, or the rate equation is R is equal to the constant again times the concentration of the reactants, hydrogen, and times the concentration of the nitrogen monoxide. This time the nitrogen monoxide is squared. Okay, now change the color so you can see this. Okay, notice there are 2 moles of hydrogen in this equation, but there is not a 2 up here. So this right here, this particular spot, does not correspond to that. There's a 2 here, but still that's coincidental that it corresponds to that coefficient. So these exponents right here, these are determined mathematically, and we're going to have to work on that. Determined with math. Okay? Alright, let's move on down. Now, here's a generic chemical equation, and this stuff that I'm giving you right now is not in your textbook, so you need to pay attention to this, and I'm going to give you examples to use that are also not in your textbook. A generic chemical equation, this A and B, little c and little d, those are the coefficients, like 2A plus 3B yields 4C plus 5D. This is what they are, the numbers in front. The rate law equation for this would be that constant again times the concentration of whatever A is. Remember, the rate law only depends on the reactants, and it's to some exponent X, and we don't know what it is yet, times the concentration of the B reactant to the exponent Y. So what we have to do is figure out what X and Y are. Okay, the X and the Y represent exponents for the concentration of the reactants. They allow you to determine how much the reaction rate changes when you increase the concentration of reactant. X is called the order of the reaction with respect to A. So this X is the order of the reaction with respect to whatever this thing is. And Y is the order of the reaction with respect to reactant B. So if you add together the X and the Y, you get the overall order of the reaction. So let's look at a couple of examples here. So first of all, let's pretend I had one. The rate is equal to the K times, let's go back up to, I'll tell you what, we'll go back up to this one up here. There's the order of a reaction with respect to hydrogen is 1, because if there's no number there, remember, in math, if there's no number there, that would be a 1. We just don't write 1s in. So I'm going to write that down there. That would be a 1. Whoops. A 1. So the x is a 1 and the y is a 2. So what's the order of this reaction with respect to hydrogen? 1. What's the order of this reaction with respect to nitrogen monoxide? 2. What's the overall order? 1 plus 2. That is a 3. That's the overall order of this reaction. Okay, that's one where we already know what those particular exponents are. All right, now we're going to write the rate law equation for this one, the general rate law equation, and then we're going to figure out the specific rate law equation for some, okay? This one says write the rate law equation, or the rate equation for this. This would be K, the constant, times the concentration of the first reactant in nitrogen to the x power, times the concentration of the second reactant, hydrogen, to the y power. And that is because the rate is determined by how much reactant you have, not how much product you have. All right, now we're going to move on into figuring out experimentally using this data to calculate the actual rate law. We're going to calculate the constants for each rate law rather, and the x and the y. Okay, here we go. Now, the first thing we need to talk about is, here's the reaction we're dealing with. This one right here. This is the net reaction. And here's the first reactant, ICl. And M is the molarity. The molar concentration. Here's the second reactant, hydrogen, again the molarity. And these are the instantaneous rates of the reaction. In a moment in time, how fast is the molarity changing in every second? So now what you have to do is we're going to first calculate the x. So we need to find, these are 3 different trials, 1, 2, and 3. We need to compare 2 trials where the concentration of only one of the reactants changes. So from this trial to here, this reactant changes and this one stays exactly the same. So that means any change in the rate is due because I changed the concentration of this. The concentration of this did not change. The ICl stayed exactly the same. The concentration of the hydrogen did change. So if the rate changed, it's because the hydrogen changed. And so now we got to figure out how much did it change. So first we look at the change. How much did it change? Well, 0.5 is twice as much as 0.25. And you can figure that out by saying 0.5 divided by 0.25 is 2. So that's the first thing, 2. 2 to the x power, because well, this one is going to be the y. 2 to the y power is equal to, so let me write down the general rate law first. The rate is equal to the K, the constant, times the concentration of ICl to some power x, times the concentration of hydrogen to some power y. Since this is the second thing, we're going to deal with the y. So the concentration between this one and this one, the second one to the first one, it was twice as much, so that's the 2. Okay? Now we look at the rates. We're going to get the value here from the rate change. So the second one minus the first one again, so we can pull up our calculator if you need to, and we turn it on, and we can see that the second one minus the first one, 0.0204, divided by the first one rather, divided by the first one, 0.0102 is going to give me that second piece. That's also a 2. Okay, so the 2 to the y power is also equal to 2. So this 2 came from 0.5 divided by 0.25, and this 2 came from 0.0204 divided by 0.0102. Now, 2 to some power y has got to equal this change. And so in math, you should understand that 2 to the first power equals itself, so that y equals a 1. So now I know what y is. Y equals a 1. Now let's figure out x. Well, I cannot use these same 2 trials because this one did not change, this one did. So I got to pick 2 more trials where the first concentration, the first reactant changed, but the second one stayed exactly the same. So in trial 2 and 3, this stayed the same, but this changed. So since this changed, this is going to be where I get my x value from. The second one divided by the first one, 0.5 divided by 0.25 is a 2. So 2 to the x power has got to equal the change in the rate over here. So this is 0.0408 divided by 0.0204, and that is also a 2. So this is an easy one. 2 to the x power has got to equal 2, so x is also equal to 1. So that's where we get our exponents from. Now let's put it into the rate equation. So the rate, now the rate is going to equal a constant times the concentration of ICl to the first power times the concentration of hydrogen to the first power. All right, now what we got, our job is to figure out K. So I pick an instantaneous rate. I pick any one of the trials. So this time I'm going to pick this one. Pick B. All right, I'm going to go and use all the information from this trial. I'm going to use a different color now. All right, first of all, the R is the rate, and since the instantaneous rate is this, that's what's going to be in the R. 0.0408 molarity per second. That's the instantaneous rate. The K is what I actually don't know. I got to calculate what my constant is. Well, what is the concentration at this instantaneous rate, at this moment in time? What was the concentration of ICl? It was 0.5 molar. So 0.5, capital M, molarity. What was the concentration of hydrogen in that moment in time? 0.5 molar. So 0.5, capital M. So now our job is just to figure out K. We got to just do the math because the only unknown is the K. All right, so let's multiply them, pull the calculator up, do our job. There, pull it back up again. All right, we're going to multiply 0.5 times 0.5. So 0.5 times 0.5 is 0.25. Okay, that's something I can put in here. So K times 0.25. Now what is M times M? M squared is equal to 0.0408 molarity per second. Now we just have to divide both sides by 0.25 M squared. Now notice numerator denominator cancel so that I have the constant, and I just have to divide 0.0408 by 0.25. So let's pull my calculator back up. 0.0408 divided by 0.25. I get 0.1632, and we have to look, we need two significant figures because 0.25 has two sig figs. So 0.16 is all I need down here. So pull this up just a smidge. There we go. 0.16. Now that takes care of this portion. But what about our unit? The unit for the constants is going to be probably the most complicated piece of this puzzle for you guys. So remember that you got to use your math skills for this. This is a complex fraction. Molarity per second divided by molarity squared. All right, now when you want to solve a complex fraction, you multiply the numerator and denominator by the reciprocal of the denominator. So 1 over m squared at the top, 1 over m squared, at the bottom and at the top. All right, that makes this go away completely. So now we have m and m squared. Well, and seconds on the bottom. All right, this m cancels with one of the m's down here, so that my unit in this case is 1. See, 1, this is 1 times 1, 1 over seconds times molarity. And that is your unit. It's weird, but that's what it is. 1 over seconds times molarity. This is equal to your K. Now that you know your K, you can write the final answer to this question, which is what is the rate law equation for this reaction? It will be the rate, the instantaneous rate, is always going to be equal to the K, which we now know what K is, 0.16, 1 over seconds times molarity. And then it's always, after that, it's always going to be equal to the concentration of whatever ICl is to the first power times the concentration of whatever hydrogen is to the first power. Now, I can always calculate the rate at this point. If I change the concentration of ICl, I just put the new concentration in here, I get a new rate. Or if I change the concentration of hydrogen, I put the new concentration in here, multiply it through, I get a new rate. I will always be able to calculate these rates now based on whatever concentration of the reactant I put into the reaction vessel. Alright, now we're going to do one more, and I know this is kind of complicated, and I did say that you can take a 3x5 card out and write as much of this on your 3x5 card as you want to, including example problems. You can use the 3x5 card on the test. You have to staple it to the test though, so I can make sure that you didn't put anything not related to this on the test. Okay, so let's do another one. We have this molecule right here, first reactant, and then the second, which is actually an ion. It should have a -1 up here. The second reactant. So the general rate would be the constant times the concentration of C4H9Br to some power x times the concentration of OH negative to some power y. So that's the general rate law, and we're going to figure out the x and the y now. So we got to look at two trials where only one of the reactant's concentration changes. So we see that this one stays the same, this one and this one are exactly the same, and this one changes. So I can use these two trials to calculate my x. So first I got to figure out the first number, and 0.2 divided, you do the second one divided by the first one, second divided by first. 0.2 divided by 0.1 is 2. So 2 to the x power equals, and then we got to do the second number comes from the rate change. So this is going to be where I get my x. So 0.002 divided by 0.001 is also a 2. So x equals 1. Alright, now we got to figure out the rate law change for the other guys. And I cannot use the second and third trial to figure out the y, because notice that the concentration changed from here to here, and the concentration changed from here to here. That means these rate law changes, we don't know what it's due to. So we have to make sure only one of them changes. So the rate, the instantaneous rate, is due only to the change of the reactant that changed. So we're eliminating variables. So what I can use though is trials 1 and 3. So in trial 1 and 3, there we go, see, it changed, but these guys stayed the same. So this changed, so any change from here to here is going to figure out your y. Alright, so 0.2 divided by 0.1, the second one divided by first one is a 2. So 2 to the y power equals 0.1 divided by 0.1. Well, that's exactly the same number. The rate didn't change. The concentration changed of this one reactant. The other reactant stayed exactly the same. This concentration changed, but the rate did not change. So what is that? 0.01 divided by 0.001 is a 1. Alright, so 2 to the y power has to equal 1. Well, in math we know that anything to the 0 power equals 1. So y has to be 0. Y has to be 0, and that is okay. So now how do I write this general rate law? It's the constant times the concentration of C4H9Br to the first power times the concentration of OH minus to the 0 power, because that's the y. Well, what is anything to the 0 power? 1. So that really means that you don't even have to deal with the hydroxide ion. So the rate law is really only equal to the constant times the change in the concentration of this first reactant. The other reactant does not matter. We can add more to it and it can't force the reaction to go faster. Alright, now that we know that, we can get rid of this component, and it kind of actually makes our math a little simpler. We're going to calculate K. I pick any trial. This time I'm going to pick trial 2. Like I said, no matter which trial you pick, you'll get the same answer. I'm going to use all the data from trial 2. All right. What is the instantaneous rate for trial 2? This. 0.0020 molarity per second. Instantaneous rate. The K is what I'm after, and what is the concentration of this reactant right here in trial 2? It's 0.2. 0.2 molar. All right, so solve K. Just divide both sides by 0.2 this time. And we're going to calculate K. You'll notice that the numerator and the denominator cancel out. All right, now I'm going to pull up the calculator. Move this over. Whoops. Do our math. 0.002 divided by 0.2. All right, 0.01. I only need one significant figure right here because there's only one significant figure in both. Well, this number, this one has two significant figures. This, so 0.01 is okay. So 0.01, that's the numbers portion, whoops, of the problem. Now we got to figure out the unit. Okay, so the unit is molarity over seconds divided by molarity. That's what this portion right here is. All right, now let's solve our complex fraction. Multiply the denominator and the numerator by the reciprocal of the denominator. This time the molarities cancel out, so you got a 1. Don't forget that. People often put just the S. There's a 1 up there, 1 and 1 down here. So 1 times 1 is a 1, and S times 1, there's a, notice this is division sign, is an S. So this is the unit for the constant this time, 1 over seconds. So now we can finally write the final equation. The rate, the instantaneous rate, is always equal to 0.01 1 over seconds, that's the constant, times the concentration of just this molecule right here. And it does not matter what I do with the hydroxide ion. This is the final answer. Okay, you're going to need to do some practice. I have some problems for you to practice on the textbook, and I'm going to give you some extra credit problems as well. Good luck.